Hi, I'm Ian. I'm studying PhD at University of Leeds, and I'm looking at how flooding is causing landslides and transport infrastructure. This is kind of something we know has happened, but looking at sort of different types and process behind it and what's causing it to happen. Here you sort of see a few different events on the left in America, in the middle in Paris, and on the right in Italy. Sort of different types of flood cause failures. And we'll sort of go through the different processes behind these different types of flood and what the effects of them are. So what's the problem is these failures are happening and we don't quite know why or what the exact processes that are happening are. And kind of an important question is, are there effects in the slope beyond failure that we're not looking at? So do the slope materials change properties with time? And why transport embankments, sort of just quickly, why not, other embankments which are also affected by the same processes? But a couple of reasons. One, they block flow pathways. So if we have rainfall above a slope, the embankment causes impoundment behind it. And also if they're built, embankments built across floodplains, when you get rainfall and river level rise and flooding, they can rise up and sort of block the water flow. So you get, again, impoundment or overtopping behind the slopes. And the second reason, they're not designed for impounding water. So there's no impermeable core in a lot of embankments. So in a lot of UK embankments, rail embankments especially, in the older ones, they were built with end tipping with no compaction. There was no kind of plan to how they're made. The materials are really variable. And that differs from something that's built with flood-specific retention, like an embankment dam, where you have an impermeable core in the slope that stops that seepage through the slope and prevents damage. So based off of this, we went out and reviewed globally failure reports of events where flooding could cause failure of transportation embankments. And we had sort of some industry input in the UK with Network Rail, but sort of a global view of literature and news reports. And from this, we took down identified four key different types of flood which are causing failure. And I'm going to sort of talk you through these and the process involved just now. So in the top left, offset head flooding, where you get a high level of water on one side of an embankment and the other. We've got overtopping on the top right, where you've got the water comes over an embankment. We've got basal floods, where the water stays at a low level at the base of the embankment and doesn't go too high. And we've got top of slope floods, where the water sits above the embankment. So first, the offset head floods, and this is kind of where you get a high water level on one side of a slope and not on the other. So, for example, where the embankment has stopped rainfall coming off a hillside, and that's what happened in this bottom picture in Italy, in Acquiava, and it failed as the train was going over the slope. Unfortunately, no serious injuries. But here, the seepage driven through the slope causes here the seepage through the slope causes process to develop like internal erosion, where you get migration of particles from one end of the slope to another, or piping to develop. There's also evidence of rapid drawdown, these sort of standard saturation processes which cause pore pressure increase and weakening and scour. Second, overtopping. This picture here is from the Conway Valley in North Wales. And this is where the river has flooded and it's overtopped the slope. And one of the main things here is you get very small failures across a large section, a large area, and you get a lot of repeated failures. Maybe not too big on their own, but together they cause quite a big impact. Thirdly, is basal floods, where you get a small flood at the bottom, and this might not necessarily cause failure on its own, but it causes increased pore pressures in the slope and scour along the bottom, and that can lead to weakening. So when you get a live load, like here on the left, the Barrow saw in the UK, or on the right in the USA, it then fails, and you don't necessarily know it's going to fail beforehand because there's no potential visible difference. But those increased pore pressures are causing a weakening in the slope and failure when loaded. And kind of D, top of slope floods, these sort of combine quite a few of the different processes we just talked about. But you get seepage through the slope, which can cause saturation, internal erosion, and you can get water going over the top as well, where you get scour and those sort of processes developing. So which is the most common? It's actually quite difficult to say, because A, you have to ask the question of what makes failure. So in this picture here from Italy, you also got one big failure in the middle, then you've got lots of smaller failures. So there's a question about how to classify that and how to set that up properly. And secondly, only the really big failures make the news in the open literature. So without sort of a deep dive into all the industry failure databases we didn't have across the world, it makes it quite hard to know how many of these are happening, especially when reopening infrastructure is the main priority for a lot of these asset managers. So in this case, getting the railway open is most important, not counting the number of individual small failures. And because of this, we chose to record the number of flood events where failure has occurred rather than the number of sort of specific failure cases. And from that, we sort of see that offset head and overtopping floods are the most common, but there's not that much difference in it. And there's going to be some bias here towards the bigger failure events that we sort of previously mentioned. So you can't sort of fully read into this because a small overtopping failure isn't going to be as accessible as a large event like this one in the picture, where it sort of makes the news or further research papers, as it was in this case. So from this, we kind of said these floods are happening and we know the processes, we know where they're happening, the different types, but kind of thought about what's happening in the slopes. And we know we get a flood and we have a slope that's got an initial strength. And then we have failure that happens during a flood, for example, due to a train passage or live loading or saturation and kind of high pore pressures, or after flood recession, so due to very like rapid drawdown where the outer slope seepage causes failure once the flood leaves. Or the other options, a slope doesn't fail. And this is kind of the key research question we had. Given there isn't failure, does the slope go back to its original strength? It could strengthen, or worse, it could weaken, and there could be some kind of permanent embankment degradation, and that might not be visible. And given that happens, when there's a future live loading or future flood event or future of a destabilization event, will the slope behave as it's expected to and as it should? And as we saw in some of the basal slope floods, this could be brought by vehicle presence, so be that trains or traffic of other sorts. Yes, like in these cases, the slope probably wouldn't fail without the embankment, but then it's coming out because of the train coming through. And the process causing this change are the main focus of the work, and primarily focused on internal erosion and other similar processes to look at what's the magnitude of the change? So is it actually significant? And then B, where in the slopes does this change occur? So is it happening at the bottom? Is it happening on the inflow side, on the outflow side? To try and sort of understand how this might affect natural changes across a slope. So the first part of this is we did some lab testing to understand the minor or the magnitude of change in stiffness, permeability, and strength. So we have made sort of some samples in sort of traxel cell was modified to have inflow from the top to the bottom of the sample to create particle movement through a slope to represent the fluid flow that you get from seepage. And then we measured using Bender elements the amount of change across a slope, across the sample, to measure shear wave velocity and similar changes. So as you haven't come across it before, internal erosion is the migration of fine particles through a sample. So when the water flow comes in this case on the left, moves to the right, the fine particles move within a matrix of the coarser particles in the soil. And this is kind of what causes those changes in soil properties and structure. You also get piping where this sort of develops further and you get full scale pipes and sort of macropores developing the slopes. And these don't necessarily come with material or slope or large scale material settlement or shrinkage. And that can be an issue for monitoring problems because you can't see where the slope changes are happening and where these problems might be occurring after flooding events. And then Bender elements, they're piezoelectric elements that allow you to measure shear wave or P wave, but mainly shear wave changes in a sample with input pulse, and you sort of measure the change in the output pulse. And this was done continuously throughout the testing, and the permeability testing was done continuously, whereas the strength changing was also done at the end of the sample tests. And from these, as you can see here in these 3 images, I'll talk you through them now, we can see changes in permeability and shear wave velocity that occur with time. So in this top one, we've got this darker line as permeability. We can kind of see that most of the change is happening at the start and then gradually flattening out towards the second half of the test. And then the dashed line, we've got changes in shear wave velocity, which we can again see reduces throughout the test, but it's a bit more up and down. And we think the primary driver of this change is the movement of fine particles from the top to the bottom of the samples. So in this case here, we've got a rapid change in permeability at the start of the test, which we think is due to the movement of the looser fine particles, which then move from the free spaces towards the pore contacts and towards the base of the sample, which creates an overall permeability reduction. Whereas the shear wave velocity measurements, that same process is happening. However, because it's a point measurement rather than a full sample measurement, you're getting much more variability because it's controlled by a specific point rather than a single section of a sample controlling the whole sample's permeability. We also see change in strength, which we think are happening for a similar reason. So in this graph at the bottom, you can see friction angle, and we've got the amount of loss, so the amount of material being washed out of the sample during the seepage process. And we kind of see a trend with this, where the more material is being washed out of a sample, the lower the friction angle is. And again, we think it's because it's creating weak zones within the sample where failure is happening. And when you then look at the shear test results for this, we see sort of a fairly normal looking failure curve, but at this lower strain at sort of 2–3%, we see a small drop. And we think that's because of localized denser zones within the sample where the particles accumulated failing before you carry on with the standard failure curve. And that's seen across most of the samples that we tested, not all, but most of them. So what's happening in the soil, this is what I was kind of talking about before, is that we have an initial sample with fine particles sort of evenly distributed within the sample. And stage 1, where material is washed from the top downwards, we get densification in this zone here. And that causes an increase in the shear wave velocity. In stage 2, we then start to see a reduction in the shear wave velocity, but the permeability continues to increase. And the reason for that is the bottom of the sample here is getting densified and becoming low permeability, but the shear wave velocity measurement point is reducing in stiffness and density. So you get a lower shear wave velocity. And depending on how those different parameters relate to each other in different parts of the sample, you get different behavior. So if we get decreases in shear wave velocity, it means the particles move from the middle to the bottom of the sample. Whereas if we get fine particle gain, we're going to get increases in shear wave velocity, but decreases in permeability. So following that, we've done a second set of tests to understand where in embankments these changes are going to occur. So we've sort of built replica slopes or replica parts of slopes with seepage from the back of the slope towards the slope toe. And we've measured the changes. We've sampled it afterwards. We've taken samples to do grain size distribution change analysis. And we also measured where the movement's happening with fluorescein sort of flowing through the slope during the tests. And what we see with this is sort of similar to what we saw in the first set of testing, is that these darker colours at the back are areas where you have an increased grain size, increased average grain size, and these shallower areas where the decreased average grain size. So it suggests that these darker areas, you're getting a source of material, and these lighter areas at the front, we're getting deposited fine grains. And we can see that going down through the slope, is that the slope the top layers of the slope, we don't see that much change. Whereas the basal layers, we're seeing quite a lot of change in material property, in average grain size distribution, which is suggesting that most of the material movement is happening at the base of the slope. The second thing we looked at is the coefficient of curvature, which is sort of a measurement of the grain size distribution within the slope. And from this, we can see that at the slope toe, we've got a slightly higher average CC. This is average across all the tests we did. And that's suggesting that as fine particle deposition here, because an increased average CC suggests the material is better graded. Whereas at the back of the slope, we have lower CC values, suggesting that the material is more poorly graded, suggesting that the material is being moved from these areas. The fine particles can move from these areas towards the slope toe. We can actually see that in the pictures of the tests when they were done. So also we can only see the edges of it, but you can see at the base here there's fines accumulation, and that's really cool because it suggests that what we're seeing in the data is actually visible in the testing as well. So it's quite nice to see that those views coming together. And you can also faintly see along here the sort of yellow section, which is the fluorescein, and that's rising up over these fines. So that's suggesting to us that this fine deposition is causing a decrease in permeability because the material is preferentially going over. And this bottom section, again, it's just reinforcing that point that with time at the back, the CC is, or in this case, the average grain distribution is higher. Whereas up towards the toe of the slope, those values are decreasing. So with time, we're seeing movement from the back towards the toe of the slope, the fine particles. So next question following this is, does this matter? Like, what's the scale of this problem? And is this actually causing any kind of noticeable effect in the slopes? So we're going to take a bit of numerical modelling, which we're still in the process of doing, so the results aren't final yet. We have the basic results from them. But in this top slope, we have a uniform material where the entire sort of embankment section, this upper section, is constructed of a material with set material parameters. Whereas in this lower slope, we've got altered materials based off the two sections of lab testing. So on the left, where the water would come in from, we've made it lose material. And on the right, where the water would flow out, we've gained material. And when we gain material, we're going to see a stiffness increase, we're going to see a density increase, we're going to see a permeability decrease. And on the left, we're going to see a reverse of that. So we're going to have a decrease in stiffness, a decrease in density, and decrease in permeability. In this top right section, we're going to not see much, so there's not changed, there's not much material movement there. And this bottom graph, these sort of lines mark up with the lines on the left-hand side. But in the uniform materials, we have quite low vibrations at the surface of the embankment when loaded with a load sort of replicating a train load. So that suggests that that's what you'd expect, really. Following change, though, the displacements are much higher. This has two issues. A, during sort of train passage, you can have vibration and and train sort of issues from that. But also there are questions about resonant frequency, which I haven't really got into in this, and how you might get sort of what basic sonic booms developing in the material following the live loading from the trains. We can see at the bottom right, it's a bit lower, where the material is denser, and that sort of matches with increased stiffness in those areas. And then what does that mean overall? It means that for slope stability, as we sort of came back to earlier, is there change following a slope, following flooding in a slope? Is there change to slope behaviour? And the answer to that is, we think yes. You know, on the right-hand side or on the inflow side, in this case the right, we're going to lose material, so we're going to increase permeability and void ratio. But on the left, where we're reducing permeability, that might create a permeability barrier, which in future flooding events or rainfall events will cause increased pore pressures on that side and a reduction in strength, which could be an issue for live loading or just generally if there's sort of significant enough destabilization events. And this might not happen after one flood event, but after 2 or 3 or 4 or 5 or 10 decades, 100 years, you might have issues there with sort of long-term stability and changes from what we think the strength of the materials are. And hopefully, with a bit of time, we'll be able to measure this in field sites. We haven't been able to because of COVID and a few other issues. But if we can do any samples and slopes that have been affected by flooding on a larger scale, then that'd be quite nice, because we might be able to see this happening and see where it's happening, how big events we actually need to cause this to happen, which is something we've not yet really looked at, sort of what's magnitude needed in the field to cause this. So kind of in conclusion, we've identified these flood events from different areas around the world. And from that, we've worked out identified and classified the different types of flooding that cause these failures and different processes involved. After flooding events, the strength of the slopes might not return to where it was initially before the floods happened. And the reason for that, or one of the reasons for that, is likely internal erosion and diffusion processes, amongst other things like wetting, drying cycles and clays, which cause changes in strength, permeability, and what have you. The changes here we've measured in permeability and stiffness are quite noticeable. There are significant changes, seeing 20% plus change in some of these properties, which really is quite significant. And that's with very small amounts of particle movement, which means you might not need that much of an event in the field to cause issues. These changes are mainly happening in the slope toe region, the base of the slope, and the water inflow surface, which is kind of what you'd expect from where you'd expect to flow for a slope, but it's nicer to see that. And these changes are significant. We can see the magnitude of change, and it's of concern, potentially, really go a bit further, but it's not like this is having no effect at all. We are sort of seeing a bit of change in the slope behaviour and the slope properties. So it sort of warrants further investigation. And that's the end, I think.